One of the most striking features of Venus is its runaway greenhouse effect. Over billions of years, Venus's proximity to the Sun and its volcanic activity caused its atmosphere to become thick with greenhouse gases, predominantly carbon dioxide. This dense atmosphere traps heat very efficiently, creating a powerful greenhouse blanket that raises surface temperatures to around 465 degrees Celsius, hot enough to melt lead. This intense heat is so extreme that it remains constant regardless of the time of day or night, making the planet the hottest in the solar system. This runaway greenhouse effect serves as a stark example of how planetary climates can spiral out of control, transforming a once potentially habitable world into a scorching, uninhabitable inferno. The surface of Venus is a testament to its volcanic past. It is covered with extensive volcanic plains, vast shield volcanoes, and numerous volcanic domes. These volcanic features reveal a history marked by widespread eruptions that have reshaped the planet's landscape repeatedly. Many of the volcanic features are relatively young in geological terms, only a few 100 million years old, indicating that volcanic activity may still be ongoing. Large shield volcanoes, some towering over 10 kilometers high, dominate the landscape, while vast lava plains stretch across much of the planet's surface. The surface is also riddled with fissures and rift zones, where tectonic forces have fractured the crust and allowed magma to reach the surface through fissures and cracks. All these features suggest that Venus has been a volcanically active world for much of its history, and some evidence hints that this activity might continue even today. Venus's atmosphere is one of the most hostile environments encountered in our solar system. Composed primarily of sulfuric acid clouds and sulfur dioxide, it creates a thick, opaque shroud that obscures the planet's surface from view in visible light. The atmosphere exerts an enormous pressure, about 92 times that of Earth's, equivalent to the pressure found deep beneath the oceans on our planet. This crushing weight, combined with the intense heat, produces conditions that are virtually impossible for humans or most known life forms to survive. The clouds are highly reflective, bouncing sunlight back into space and giving Venus its bright appearance when viewed from Earth, but they also trap enormous amounts of heat, contributing to the planet's extreme surface temperatures. The atmosphere is also characterized by powerful winds that can reach speeds of hundreds of kilometers per hour. These winds circulate the planet in just a few days, creating a phenomenon known as superrotation, where the atmosphere moves much faster than the planet itself. This leads to turbulent weather patterns and complex atmospheric dynamics, making Venus a dynamic and volatile environment. Despite the thick cloud cover, scientists have used radar instruments to peer through the clouds and map the surface in detail, revealing a landscape shaped by volcanic activity and tectonic forces. A particularly intriguing aspect of recent planetary science revolves around the detection of phosphine gas in Venus's atmosphere. Phosphine, a simple molecule composed of phosphorus and hydrogen, is associated on Earth with biological processes, especially in environments devoid of oxygen, such as swamps and deep-sea vents. Its presence on Venus was first announced in 2020 based on observations made with powerful telescopes. This discovery sparked widespread excitement because phosphine is difficult to produce through known non-biological processes under Venusian conditions. The detection raised the tantalizing possibility that microbial life could exist in the planet's upper clouds, where temperatures and pressures are less extreme than on the surface. However, subsequent studies and analyses have cast doubt on the initial findings, and scientists are still working to verify whether phosphine truly exists in Venus's atmosphere or if the signals were artifacts of observational challenges. The mystery remains alive, fueling ongoing research and future missions aimed at unraveling this enigma. Venus continues to hold many secrets. Questions about whether the planet is still geologically active, how its climate evolved so drastically, and whether its clouds might harbor life remain unanswered. Several upcoming missions are planned to explore these mysteries more deeply. NASA's Veritas spacecraft aims to produce high-resolution maps of the planet's surface, seeking evidence of recent volcanic activity and better understanding its geological history. The European Space Agency's Envision mission will investigate Venus's atmosphere and surface, focusing on volcanic activity and the planet's internal structure. Additionally, proposals for balloon or drone missions intend to study the cloud layers directly, searching for chemical signatures or signs of life. Venus stands as a powerful reminder of the fragility and diversity of planetary environments. Its extreme greenhouse effect, volcanic landscape, and toxic atmosphere serve as cautionary examples of how climate and geological processes can dramatically transform a planet. Yet at the same time, Venus continues to intrigue scientists, prompting new questions and inspiring future exploration. Studying this hellish world not only helps us understand planetary evolution, but also offers vital insights into the potential consequences of climate change, both on Earth and beyond. Mars, often called the Red Planet because of its distinctive reddish appearance caused by iron oxide on its surface, has fascinated humanity for centuries. Its surface features are diverse and include massive volcanoes, deep canyons, impact craters, and ancient riverbeds, revealing a planet shaped by both volcanic activity and water erosion over billions of years. One of the most prominent surface features is Olympus Mons, the tallest volcano in the solar system, towering about 22 kilometers high. Nearby are other large volcanoes, forming a volcanic plateau that highlights Mars's volcanic past. The planet also hosts Valles Marineris, an immense canyon system stretching over 4,000 kilometers, about the length of the United States, and reaching depths of up to 7 kilometers, which suggests significant tectonic and erosional processes. Mars's surface is also marked by vast plains, impact craters from collisions with asteroids, and layered sedimentary deposits that hint at a wetter and possibly habitable past. These features suggest that Mars once had a dynamic climate with conditions that could have supported liquid water on its surface. The exploration history of Mars began with flyby missions in the 1960s, such as NASA's Mariner spacecraft, which provided the first close-up images and data about the planet. Subsequent missions included orbiters like Mars Odyssey and Mars Reconnaissance Orbiter, which have mapped the surface and analyzed mineral compositions. Landers such as Viking 1 and Viking 2 in the 1970s conducted experiments on surface conditions, while the two rovers, Spirit and Opportunity, launched in the 2000s, greatly advanced our understanding by exploring terrain, analyzing rocks, and searching for signs of water and past life. More recently, NASA's Curiosity rover, which landed on Mars in 2012, has been investigating Gale Crater. It has analyzed rocks and soil to determine Mars's past environmental conditions, finding evidence of ancient lakes and streams, and confirming that the planet once had the necessary ingredients for life. The Curiosity rover continues to explore and analyze the planet's geology and climate. The newer Perseverance rover, which landed in Jezero Crater in 2021, is on a mission to seek signs of ancient microbial life and collect rock samples for future return to Earth. Perseverance is also testing new technologies, including the first helicopter on another planet, Ingenuity, which has demonstrated the potential for aerial exploration on Mars. Evidence of past water on Mars is abundant and compelling. Images and mineral analyses have revealed dried-up riverbeds, lake beds, and minerals that only form in the presence of liquid water, such as clays and sulfates. These findings suggest that Mars was once warm and wet, with conditions that could have supported microbial life. Looking to the future, scientists and space agencies like NASA and private companies are optimistic about the possibility of colonizing Mars. Plans include establishing sustainable habitats, growing food, and utilizing local resources, a process called in situ resource utilization, to support human explorers. The goal is to learn how humans can live and work on another planet paving the way for potential long-term settlements and further exploration of the solar system. Mars continues to be a focus of scientific curiosity and exploration, with each mission bringing us closer to understanding its history, climate, and potential for future human habitation. The discoveries made by rovers like Curiosity and Perseverance are crucial stepping stones toward turning humanity's dream of exploring and perhaps someday colonizing the red planet into reality. Mercury stands out as one of the most intriguing planets in our solar system due to its unique physical and geological characteristics. Its extreme proximity to the Sun exposes it to intense solar radiation, leading to drastic temperature fluctuations on its surface, soaring to scorching heights during the day and plummeting to freezing lows at night. These extreme temperature changes create a hostile environment, making Mercury a challenging subject for exploration and study. The planet's surface is a testament to its tumultuous history. It bears the scars of billions of years of impacts from asteroids and comets, leaving behind a landscape dotted with craters, vast plains, and towering cliffs. Notably, features like the Caloris Basin reveal the planet's violent past and the colossal impacts it has endured. The composition of Mercury's surface, rich in metals such as iron and nickel, contributes to its dense metallic core, which profoundly influences its magnetic properties. One of the most fascinating aspects of Mercury is its magnetic field. Despite being a small planet, Mercury generates a magnetic field that, although weaker than Earth's, is significant in its own right. This magnetic field indicates that Mercury's core is at least partially molten and actively convecting, creating a planetary dynamo. This magnetic environment not only protects parts of the planet from solar wind, but also results in phenomena like auroras near the poles, offering valuable insights into planetary magnetic processes that are applicable across the solar system. Our understanding of Mercury has advanced considerably through space missions. The NASA's Messenger spacecraft provided detailed observations of its surface, magnetic field, and exosphere, greatly enriching our knowledge about its composition, internal structure, and geological history. Building upon these findings, the European Space Agency's Bepi-Colombo mission was launched to conduct further detailed studies. This upcoming mission aims to explore Mercury's magnetic environment, surface features, and internal dynamics more comprehensively, potentially unlocking answers to long-standing questions about the planet's formation and evolution. Looking ahead, scientists are considering even more ambitious missions, including potential landers and surface explorers that could directly analyze the planet's geology and environment. Such missions would provide invaluable data, helping to unravel the mysteries of Mercury's origin, its large metallic core, and the history of its magnetic field. These efforts are crucial not only for understanding Mercury itself, but also for gaining broader insights into the processes that shape rocky planets throughout the universe. In essence, Mercury remains a small yet profoundly significant world that offers a window into planetary formation, internal geodynamics, and the effects of solar proximity. Its extreme environment, unique magnetic properties, and rich geological history make it a subject of continual scientific interest. As technological capabilities grow and new missions are launched, our knowledge of this enigmatic planet will deepen, enriching our understanding of the complex dynamics that govern our solar system. Jupiter, the largest planet in our solar system, stands out as an awe-inspiring world characterized by its immense size, dynamic atmosphere, complex moon system, and powerful radiation belts. As a gas giant, Jupiter's mass is so enormous that it accounts for more than 2/3 of the total planetary mass in our solar system. Its sheer volume is staggering, so much so that it could contain over 1,000 Earths within its gaseous bounds. This colossal size influences its gravitational pull, which strongly affects nearby objects and shapes the entire solar system. One of Jupiter's most striking features is its turbulent and colorful atmosphere, which is composed primarily of hydrogen and helium. The planet's atmosphere is layered with swirling clouds, storms, and jet streams that move at incredible speeds. Among these atmospheric phenomena, the most famous and enduring feature is the Great Red Spot, a massive, persistent storm that has been raging for at least hundreds of years. This enormous storm, larger than Earth itself, is a high-pressure anticyclonic system characterized by its reddish hue, which may result from complex chemical reactions involving compounds like phosphorus or sulfur. The Great Red Spot's size and longevity make it a unique feature in planetary science, providing insight into atmospheric dynamics in a gas giant environment. Surrounding this iconic storm are numerous other smaller storms and turbulent cloud bands, creating a constantly changing and vibrant spectacle. Jupiter's moon system is one of the most intriguing aspects of the planet. It hosts a diverse array of natural satellites. Over 70 moons have been observed, with 4 of them being particularly notable: Io, Europa, Ganymede, and Callisto. These moons vary widely in size, composition, and geological activity. Io is the most geologically active body in the solar system, dotted with hundreds of volcanoes that regularly erupt, spewing sulfur and other volcanic materials into space. Europa, on the other hand, is believed to harbor a subsurface ocean beneath its icy crust, making it a prime candidate in the search for extraterrestrial life. Ganymede is the largest moon in the solar system, even bigger than Mercury, and features a mixed surface of ice and rock, along with its own magnetic field. Callisto, heavily cratered and ancient, offers a window into the early solar system's history. These moons are not only fascinating objects of study, but also serve as potential locations for future exploration and the search for life beyond Earth. Jupiter's powerful radiation belts are another remarkable feature. The planet's magnetic field, which is generated by the movement of metallic hydrogen within its interior, creates a vast and intense magnetosphere that traps high-energy particles. These radiation belts are much stronger than Earth's Van Allen belts and pose significant challenges for spacecraft missions. The radiation environment around Jupiter can be deadly to unshielded spacecraft and requires specially designed technology to study the planet and its moons safely. The magnetosphere also gives rise to stunning auroras near the planet's poles, bright, colorful displays caused by charged particles colliding with the planet's upper atmosphere, similar to Earth's northern and southern lights, but far more energetic and extensive. In summary, Jupiter is a colossal world that exemplifies the grandeur and complexity of our solar system's gas giants. Its massive size influences every aspect of its physical nature, from its turbulent atmosphere and enduring storms like the Great Red Spot to its extensive and diverse moon system. The planet's intense radiation belts and magnetic fields add another layer of intrigue, making Jupiter not only a subject of scientific curiosity, but also a key to understanding planetary processes, magnetic phenomena, and the potential for habitability in extreme environments. As ongoing missions like the Juno spacecraft continue to explore Jupiter in greater detail, our understanding of this giant planet deepens, revealing the intricate and dynamic nature of worlds beyond Earth. Saturn, the sixth planet from the Sun, is renowned across the solar system for its breathtaking and intricate ring system, making it one of the most visually stunning planets to observe. As a gas giant, Saturn is primarily composed of hydrogen and helium, much like Jupiter, but it is distinguished by its extensive and luminous rings that have captivated astronomers and the public alike for centuries. These rings are not only a defining characteristic, but also a complex and dynamic feature that reveals much about planetary ring systems and celestial mechanics. The iconic rings of Saturn are composed of countless particles ranging in size from tiny dust grains to large chunks of ice and rock. These particles orbit the planet in a thin, flat plane, creating a shimmering, multi-layered structure that extends thousands of kilometers outward from the planet. The rings are divided into several main sections, labeled alphabetically in order of their discovery, such as the A, B, and C rings, each with unique properties and compositions. The most prominent and brightest of these is the B ring, which is dense and opaque, while the A ring is characterized by its distinct gaps, including the famous Cassini division, a large dark gap between the A and B rings. The rings are primarily made of water ice, which reflects sunlight and gives them their brilliant appearance, but they also contain darker, less reflective material. The rings of Saturn are not static. They are constantly evolving due to gravitational interactions, collisions among particles, and the influence of Saturn's moons. These interactions create waves, braids, and spokes within the rings, making them a natural laboratory for studying planetary ring dynamics. The origin of Saturn's rings remains a subject of scientific investigation, with theories suggesting they could be remnants of a shattered moon, debris from comets, or material that never coalesced into a moon. The Cassini-Huygens mission, launched in 1997 and arriving at Saturn in 2004, has revolutionized our understanding of this majestic planet and its rings. Over its 13-year mission, Cassini provided a wealth of data, capturing detailed images and conducting extensive studies of the ring structures, their composition, and their interactions with Saturn's moons. One of its key discoveries was the identification of complex ring features, including propeller-shaped disturbances caused by embedded moonlets, and the detection of organic molecules within the rings, hinting at prebiotic chemistry. Cassini also observed the dynamic behavior of the rings, noting their seasonal changes and the influence of Saturn's gravitational field, which helped scientists understand the longevity and evolution of ring systems. Beyond the rings, Cassini's exploration of Saturn's moons has yielded extraordinary discoveries. Among these, Titan and Enceladus stand out as some of the most compelling worlds in the solar system, each offering tantalizing clues about the potential for life beyond Earth. Titan, Saturn's largest moon, is an enigmatic world shrouded in thick orange haze composed of complex organic molecules. Its dense atmosphere is primarily nitrogen, with traces of methane and other hydrocarbons, creating a landscape that resembles an early Earth environment. Cassini's observations revealed lakes and seas of liquid hydrocarbons, mainly methane and ethane, on Titan's surface, as well as vast, river-like networks carved into the icy crust. These features make Titan a prime candidate for studying prebiotic chemistry and the processes that could lead to life. The moon's surface is a mixture of water ice and organic-rich sediments, and its thick atmosphere facilitates complex chemical reactions. Cassini also discovered cryovolcanoes, ice volcanoes that erupt water, ammonia or methane instead of lava, indicating active geological processes beneath Titan's icy crust. Enceladus, a smaller but equally fascinating moon, captured scientists' attention with its stunning plumes of water vapor and ice particles erupting from its south polar region. These plumes suggest the presence of a subsurface ocean of liquid water, kept warm by tidal heating caused by gravitational interactions with Saturn and other moons. Cassini's flybys confirmed that Enceladus's ocean is in contact with its rocky core, creating conditions potentially suitable for microbial life. The moon's surface is covered with bright, reflective ice, and the plumes contain organic molecules, salts, and other chemicals necessary for life. The discovery of hydrothermal activity at the ocean floor, similar to Earth's deep-sea vents, further enhances Enceladus's status as a prime candidate in the search for extraterrestrial life in our solar system. The scientific community has been profoundly influenced by the discoveries made by Cassini. The mission has not only expanded our understanding of Saturn's complex system of rings and moons, but also provided critical insights into planetary processes, the potential habitability of icy worlds, and the origins of organic molecules in space. The data collected continue to inspire new theories and missions aimed at exploring these intriguing environments further. Saturn remains one of the most captivating planets in our solar system, thanks to its stunning rings and the rich diversity of its moons. Its iconic rings, formed of countless icy particles, exemplify the beauty and complexity of planetary ring systems, while the discoveries by the Cassini mission have unveiled secrets of its enigmatic moons, Titan and Enceladus, that could reshape our understanding of life's potential beyond Earth. As future missions and technologies are developed, scientists look forward to uncovering even more about this magnificent planet and its diverse family of worlds, deepening our appreciation for the intricate and dynamic nature of our cosmic neighborhood. Uranus, the seventh planet from the Sun, is one of the most intriguing and enigmatic worlds in our solar system. As a member of the ice giant class, Uranus presents a set of unique characteristics that distinguish it from its fellow giants, Jupiter and Saturn. Its distinctive features, including its extreme axial tilt, predominantly icy composition, and the relative scarcity of detailed exploration, have made Uranus a subject of ongoing scientific interest and mystery. One of Uranus's most striking features is its extraordinary axial tilt. Unlike most planets in the solar system, which rotate roughly upright relative to their orbital planes, Uranus is tilted on its side at an angle of approximately 98 degrees. This means that its rotational axis is nearly parallel to its orbital plane, with the planet essentially rotating on its side. This extreme tilt results in unusual seasonal patterns. Each pole gets around 42 years of continuous sunlight, followed by 42 years of darkness as Uranus orbits the Sun. This peculiar orientation is believed to be the result of a massive collision or series of collisions with other celestial bodies early in the planet's history, which knocked Uranus onto its side, drastically altering its rotational dynamics. Uranus's tilted axis has profound implications for its atmospheric and climatic systems. The planet experiences seasonal changes that are more extreme and elongated than those of other planets, leading to unique weather patterns and possibly affecting the composition and behavior of its atmosphere. The tilt also influences the orientation of its magnetic field, which is notably offset and tilted relative to the planet's rotational axis, adding another layer of complexity to its magnetic environment. In terms of composition, Uranus is classified as an ice giant because it contains a higher proportion of ices, substances like water, ammonia, and methane, mixed with its hydrogen and helium atmosphere. Unlike Jupiter and Saturn, which are primarily composed of gaseous hydrogen and helium, Uranus's interior is believed to contain a thick mantle of icy materials surrounding a rocky core. The atmosphere of Uranus is relatively thin and composed mostly of hydrogen, helium, and methane gas, which gives the planet its characteristic pale blue color. The methane molecules absorb red light and reflect blue, resulting in its distinctive hue. Beneath the atmosphere, high-pressure ices and fluids comprising water, ammonia, and methane exist in a supercritical state, forming an exotic and less understood layer that behaves differently from typical liquids or solids. Despite its fascinating characteristics, Uranus remains one of the least understood planets in our solar system. There are several reasons for this relative mystery. Limited exploration. To date, Uranus has been visited by only one spacecraft, Voyager 2, which flew past the planet in 1986. Voyager 2 provided valuable data on Uranus's atmosphere, magnetic field, rings, and moons, but the flyby was brief, and many questions remain unanswered. Since then, no dedicated mission has returned to Uranus, leaving much of its environment and internal structure unexplored. Difficult to reach. The planet's distance from Earth, about 2.9 billion miles, 4.6 billion kilometers, makes sending missions there challenging and costly. The long travel times and the need for specialized spacecraft technology have hindered the development of more extensive observational missions. Unusual magnetic field. Uranus's magnetic field is atypical, highly tilted and offset significantly from the planet's center. This irregularity complicates our understanding of its internal structure and the dynamo processes generating its magnetic field. Studying the magnetic environment requires close-up measurements that current knowledge cannot provide. Complex atmospheric dynamics. The atmospheric processes of Uranus are less well understood compared to those of Jupiter and Saturn. Its relatively featureless, pale appearance suggests a calmer atmosphere with fewer visible storms and turbulence, but this may also be due to observational limitations. The seasonal and axial effects add complexity to understanding its atmospheric circulation. Uncertain internal structure and composition. The precise layering, composition, and dynamics of Uranus's interior remain subjects of scientific modeling and speculation. Without in situ measurements, scientists rely on remote sensing and theoretical models, which can only approximate the planet's true internal conditions. Given these challenges, Uranus remains a compelling target for future exploration. A dedicated mission could help unravel its internal structure, magnetic field, atmospheric dynamics, and the composition of its mysterious icy mantle. Such a mission would provide critical insights not only into Uranus itself, but also into the broader class of ice giants, which are common in exoplanetary systems beyond our own. In summary, Uranus's extreme tilt, icy composition, and the scarcity of detailed data contribute to its reputation as one of the most poorly understood planets in the solar system. Its unique orientation and composition offer a natural laboratory for studying planetary formation, magnetic dynamo processes, and atmospheric dynamics under conditions unlike those on more familiar planets. As technology advances and interest in outer solar system exploration grows, future missions to Uranus promise to shed light on these mysteries, deepening our understanding of this distant icy world. Neptune, the eighth and most distant planet from the Sun, remains one of the most fascinating and dynamic worlds in our solar system. As an ice giant, Neptune exhibits a remarkable combination of intense atmospheric activity, a vivid methane-rich atmosphere, and a complex magnetic environment that continues to intrigue scientists. Neptune's atmosphere is primarily composed of hydrogen and helium, but it is distinguished by a significant presence of methane gas. This methane absorbs red and infrared light from the Sun, reflecting back mainly blue wavelengths, which gives the planet its striking deep blue appearance. The atmosphere is layered with clouds and haze, creating a highly dynamic and turbulent environment. Beneath the visible cloud tops lies a deep interior filled with hot, dense fluids and ices, mainly water, ammonia, and methane, that surround a rocky core. While the specifics of Neptune's internal composition are still being studied, current models suggest a complex structure with significant convective activity. One of Neptune's most notable features is its extraordinarily powerful winds. These winds are among the fastest observed in the solar system, reaching speeds up to about 2,100 kilometers per hour, roughly 1,300 miles per hour. Such extreme velocities drive vigorous weather patterns, including massive storms and high-altitude clouds. The famous Great Dark Spot, observed by Voyager 2 in 1989, was a colossal storm system comparable in size to Earth. Although this particular storm eventually dissipated, Neptune continues to host similar transient storms, indicating a highly energetic atmosphere. Unlike Jupiter's long-lasting Great Red Spot, Neptune's storms tend to be short-lived and highly variable, reflecting the planet's intense atmospheric turbulence. The internal heat of Neptune plays a vital role in fueling its atmospheric phenomena. Interestingly, Neptune emits more energy than it receives from the Sun, which contributes to the high-speed winds and storm activity seen today. This internal heat source is somewhat surprising given the planet's distance from the Sun, highlighting the complex thermal dynamics within Neptune. The most comprehensive data on Neptune came from NASA's Voyager 2 spacecraft, which flew past the planet on August 25, 1989. Voyager 2's flyby provided invaluable insights, capturing detailed images of Neptune's cloud features, storms, and atmospheric composition. The spacecraft revealed the existence of the Great Dark Spot and documented numerous bright clouds composed of methane ice crystals, which indicated vigorous convection within the atmosphere. Voyager 2 also measured the planet's wind speeds and provided the first detailed look at its magnetic field, which is notably tilted and offset from Neptune's center, a feature that adds complexity to understanding its internal dynamo processes. Additionally, Voyager 2 confirmed the existence of a faint ring system composed of dust particles and offered clues about Neptune's magnetic environment. Despite these rich discoveries, Neptune remains one of the least explored planets in our solar system. Its extreme distance from Earth, about 4.5 billion kilometers, roughly 2.8 billion miles, poses significant challenges for space exploration. The high costs and long travel times have limited the development of dedicated missions to Neptune following Voyager 2's flyby. Consequently, many questions about Neptune's internal structure, atmospheric dynamics, and magnetic field remain unanswered. Its complex and transient weather phenomena are difficult to study remotely, and the planet's internal composition and heat flow are inferred through models rather than direct measurements. The unique nature of Neptune's magnetic field, which is highly tilted and offset from the planet's center, complicates understanding the planet's interior and dynamo mechanisms. Additionally, the variability in atmospheric storms and high wind speeds makes predicting and studying Neptune's weather systems a significant scientific challenge. Future exploration of Neptune holds great promise. Several mission proposals aim to send new spacecraft to study the planet in greater detail, which would help uncover the mysteries of its atmosphere, magnetic field, and internal structure. Such missions could significantly enhance our understanding of planetary formation and evolution, especially for ice giants, which are common in exoplanetary systems. In essence, Neptune exemplifies a world of extremes. Its fierce winds, vibrant methane atmosphere, and complex magnetic environment make it a captivating subject of scientific inquiry. Although Voyager 2 provided a foundational glimpse into this distant world, much about Neptune remains to be explored. Continued interest and future missions are essential to unlocking the secrets of this distant icy giant, broadening our understanding of planetary diversity and the processes that shape our solar system. Pluto, once the 9th planet in our solar system, has had a fascinating and tumultuous history. From its discovery to its reclassification and the groundbreaking New Horizons mission, Pluto's story is one of intrigue, exploration, and a deeper understanding of our celestial neighborhood. Discovery and initial classification. Pluto was discovered on February 18, 1930, by American astronomer Clyde Tombaugh at Lowell Observatory in Flagstaff, Arizona. Initially considered the 9th planet in our solar system, Pluto was found to have an unusual orbit, which was thought to be caused by its gravitational influence on Neptune. The discovery of Pluto was met with excitement and curiosity, with many speculating about its composition and size. A planetary census. For decades, Pluto was considered a full-fledged planet, alongside Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. However, as more was learned about Pluto and other objects in the Kuiper Belt, a region of icy bodies beyond Neptune's orbit, astronomers began to question Pluto's planetary status. In the early 2000s, the discovery of other objects in the Kuiper Belt, similar in size and composition to Pluto, raised doubts about its uniqueness as a planet. Reclassification. In 2006, the International Astronomical Union, IAU, formed a committee to redefine the term planet. After much debate and discussion, the IAU adopted a new definition that would reclassify Pluto as a dwarf planet. According to this definition, a planet is a celestial body that is in orbit around the Sun, has sufficient mass to assume a hydrostatic equilibrium shape, and has cleared the neighborhood around its orbit. Pluto does not meet the third criterion, as its orbit overlaps with other objects in the Kuiper Belt. Instead of being considered a full-fledged planet, Pluto was reclassified as a dwarf planet, a new category created by the IAU. New Horizons mission. In 2006, NASA launched the New Horizons spacecraft to study Pluto and the Kuiper Belt. After a 9.5-year journey, New Horizons flew within 7,800 miles of Pluto on July 14, 2000. Some of the key findings from the New Horizons mission include geological activity on Pluto's surface, with evidence of recent tectonic activity and possible cryovolcanism. Pluto's surface is composed primarily of nitrogen ice mixed with darker organic material. The atmosphere is thin and composed mainly of nitrogen gas. New Horizons discovered 5 moons orbiting Pluto: Charon, Nix, Hydra, Kerberos, and Styx. The mission also detected a possible ring system around Pluto. What we learned from New Horizons. The New Horizons mission has greatly expanded our knowledge of Pluto and the Kuiper Belt. Some of the key takeaways from the mission include the diversity of solar system objects and the geological activity on small bodies. The mission provided insights into Pluto's composition and evolution, shedding light on how small bodies in the Kuiper Belt formed and evolved over billions of years. New Horizons has also highlighted the importance of ongoing research and discovery in understanding our celestial neighborhood. As we continue to explore our solar system and beyond, we are reminded of the complexity and richness of our cosmos. The reclassification of Pluto has sparked ongoing debate among scientists and the public. While some argue that Pluto's unique characteristics make it a planet in its own right, others see it as an important part of a larger family of dwarf planets in the Kuiper Belt. Ceres in the asteroid belt, an in-depth overview. Ceres is the largest object in the asteroid belt, situated between the orbits of Mars and Jupiter. It is classified as a dwarf planet due to its size and shape, but is also considered an asteroid because of its composition and location. Discovered in 1801 by Giuseppe Piazzi, Ceres has long intrigued scientists because of its unique features and what they reveal about the early solar system. Geology of Ceres. The surface of Ceres is a complex mosaic of terrains that tell a story of geologic activity and evolution. It exhibits both heavily cratered regions and areas that are surprisingly smooth, indicating different geological processes at work over time. The surface is primarily composed of water ice mixed with hydrated minerals that contain water within their crystal structure. These include clay minerals and salts such as magnesium sulfate and sodium carbonate. Ceres has a differentiated interior, meaning it has distinct layers. Its core is believed to be rocky, surrounded by a mantle of water ice and possibly an underground liquid water layer. Evidence suggests that internal processes may still be ongoing, such as cryovolcanism, volcanic activity involving the eruption of brine or icy materials instead of molten rock. Features like mountain-like structures and surface fractures support the idea of internal stress and activity that has shaped its landscape. The surface also contains signs of past and possibly current geological activity, including tectonic features and areas where the crust may have cracked or shifted. The presence of salts and hydrated minerals indicates that liquid water, either in the past or still today, has played a significant role in modifying Ceres' surface. Bright spots on Ceres. One of the most captivating features of Ceres is the discovery of bright spots, especially within the crater known as Ocata. These bright spots are a stark contrast to the surrounding darker terrain and have fascinated scientists and the public alike. The bright spots are primarily composed of sodium carbonate salts, which are believed to have been deposited by water that once reached the surface, then evaporated, leaving behind mineral deposits. The origin of these salts suggests that liquid water or brine has interacted with the surface relatively recently in geological terms. The bright spots are thought to be the result of endogenic activity, internal processes that brought material from beneath the surface to the exterior. The presence of these salts and bright deposits hints that Ceres may still be geologically active or has experienced recent activity. This activity could involve pockets of liquid water or brines moving upward through cracks and reaching the surface, then evaporating and leaving behind the salts that form the bright spots. The possibility of a subsurface ocean. One of the most intriguing aspects of Ceres is the evidence suggesting it might harbor a subsurface ocean beneath its icy crust. Data from NASA's Dawn spacecraft, which orbited Ceres from scientists, have observed water vapor plumes emanating from Ceres, along with the detection of hydrated salts on its surface. These findings imply that liquid water or brines could exist beneath the crust, kept in a liquid state by internal heat. The heat may originate from radioactive decay within the rocky core or residual heat from Ceres formation. The existence of a layered internal structure, rocky core, water ice mantle, and a possible liquid water layer is consistent with models of small planetary bodies that have retained internal heat. If a subsurface ocean exists, it would be an important target for astrobiology, as such environments could potentially support microbial life. The presence of salts and the chemical interactions between water and minerals increase the potential habitability of these hidden water reservoirs. Significance and future research. Ceres is a key object of interest because it bridges the gap between small rocky bodies and larger planetary bodies with complex geology. Its surface features, bright salts, and potential subsurface ocean make it a prime candidate for understanding the processes of planetary differentiation, cryovolcanism, and the evolution of water in the solar system. Future missions and observations aim to better understand the composition, internal structure, and activity of Ceres. These studies could answer fundamental questions about the presence of liquid water beneath small bodies, their potential to host life, and their role in the broader context of planetary science. Ceres is a fascinating celestial body in the asteroid belt with a diverse and dynamic geology. Its bright spots, composed of salts deposited by water, suggest recent or ongoing internal activity. The possibility of a subsurface ocean beneath its icy crust raises exciting prospects for astrobiology and our understanding of water distribution in the solar system. Ongoing research continues to uncover the secrets of this intriguing dwarf planet, making Ceres an essential object of study in planetary science. Europa, one of Jupiter's 4 largest moons and a prominent member of the Galilean satellite family, has captivated scientists and explorers for decades due to its intriguing surface features and the compelling possibility of harboring a vast subsurface ocean beneath its icy exterior. The moon's surface is remarkably smooth and young-looking, characterized by a complex network of cracks, ridges, and chaotic terrains that suggest active geological processes. This icy shell, estimated to be around 15 to 25 kilometers thick, is primarily composed of water ice, but it also contains salts and chemical residues that hint at ongoing interactions with liquid water beneath. The surface features, such as extensive fractures and ridges, are believed to result from tidal stresses exerted by Jupiter's gravitational pull, which flexes the ice shell and generates internal heat. This tidal heating not only maintains the structural integrity of the ice, but also provides the energy needed to sustain a global subsurface ocean, possibly hundreds of kilometers deep. Evidence from multiple missions, including the Galileo spacecraft, has indicated that beneath this icy crust lies a salty, liquid water ocean that remains in a liquid state due to the immense pressure from the overlying ice and the internal heat generated by tidal flexing. The presence of salts like magnesium sulfate and sodium chloride on the surface further supports the idea that this ocean is chemically rich and potentially habitable, offering essential nutrients and energy sources that could support microbial life. The detection of induced magnetic fields around Europa by the Galileo orbiter provided some of the strongest evidence for a conductive, salty ocean beneath the ice, as variations in the magnetic field suggest the movement of a liquid layer below the crust. This subsurface ocean is believed to be in contact with Europa's rocky mantle, creating the potential for chemical exchanges that could resemble conditions found at deep-sea hydrothermal vents on Earth, where life thrives without sunlight. The prospect of a liquid ocean beneath Europa's ice shell has profound implications for astrobiology, as it raises the possibility of an environment where life might exist in the absence of surface conditions similar to those on Earth. Recognizing the importance of Europa as a prime candidate for extraterrestrial life, NASA has developed the Europa Clipper mission, which is scheduled to launch in the mid-2020s and aims to conduct detailed reconnaissance of the Moon's surface and interior. The spacecraft will carry a suite of sophisticated instruments designed to analyze surface composition, map the thickness and properties of the ice shell, and detect any water vapor plumes that might be escaping from the subsurface ocean through cracks and fissures. These plumes, similar to geysers observed on other icy moons like Enceladus, could provide direct samples of the ocean's material, allowing scientists to analyze its chemical makeup and assess its habitability. The Europa Clipper's objectives include investigating the thickness of the ice shell to determine how accessible the ocean might be for future missions, studying surface features to understand the Moon's geological activity, and analyzing the chemical environment to evaluate its potential for supporting life. Equipped with high-resolution cameras, ice-penetrating radar, spectrometers, magnetometers, and thermal imagers, the spacecraft will generate detailed maps and data that will help scientists unravel the complex interactions between Europa's surface and subsurface environments. The insights gained from this mission are expected to revolutionize our understanding of Europa's internal dynamics, its capacity to support life, and the broader implications for habitability in icy worlds across our solar system. As we stand on the cusp of this new era of exploration, Europa remains a symbol of scientific curiosity and hope, embodying the tantalizing possibility that beneath its frozen exterior lies a hidden ocean teeming with potential life, waiting to be uncovered by the dedicated endeavors of future space missions. Titan, Saturn's largest moon, is one of the most fascinating celestial bodies in our solar system due to its dense, thick atmosphere and complex surface features that resemble some of the early conditions of Earth. Its atmosphere is primarily composed of nitrogen, similar to Earth, but it also contains a significant amount of methane, which plays a crucial role in shaping its environment. The atmosphere is incredibly dense and opaque, with a surface pressure about 1.5 times that of Earth at sea level, creating a persistent haze of organic molecules and aerosols that obscure direct observation of the surface from space. This thick, hazy atmosphere traps heat and extends several hundred kilometers above the surface, making Titan one of the coldest places in the solar system, with surface temperatures averaging around -79 degrees Celsius. Beneath this chilly exterior, Titan boasts a complex landscape of lakes, rivers, and seas filled with liquid methane and ethane, making it the only other known body in the solar system besides Earth to have stable surface liquids. These hydrocarbon lakes are scattered across the polar regions, forming vast, dark, and smooth expanses that are constantly shaped and reshaped by seasonal changes and atmospheric processes. The presence of lakes filled with methane and ethane is particularly intriguing because these hydrocarbons can exist in liquid form at Titan's frigid temperatures, creating an environment vastly different from Earth's water-based ecosystems. The chemistry of Titan's atmosphere and surface is rich with organic molecules produced through photochemical reactions driven by sunlight and energetic particles from Saturn's magnetosphere. These complex organic compounds, sometimes called tholins, settle onto the surface, contributing to the Moon's orange-brown haze and potentially forming the building blocks of life. While the surface conditions are extremely cold and seemingly inhospitable to life as we know it, the possibility of subsurface environments, such as underground liquid water oceans or reservoirs, has sparked scientific interest in Titan as a potential habitat for extraterrestrial life. Some hypotheses suggest that within Titan's icy crust there could be liquid water mixed with ammonia, providing an environment where chemical reactions necessary for life might occur, protected from the harsh surface conditions. The presence of organic molecules combined with the potential for subsurface liquid water raises the exciting possibility that Titan could host some form of microbial life, especially in environments where chemical energy sources are available for metabolism. Future missions, like the upcoming Dragonfly drone, aim to explore Titan's surface in detail, studying its organic chemistry, surface geology, and potential habitability. By flying across Titan's diverse landscapes, Dragonfly will analyze surface materials directly, searching for chemical signatures that could point to prebiotic or even biological processes. Scientists remain captivated by Titan's unique environment as it offers a natural laboratory to study complex organic chemistry and assess the potential for life in worlds vastly different from Earth. While the extreme cold and hydrocarbon lakes pose significant challenges for life as we know it, Titan's rich organic chemistry and subsurface possibilities make it one of the most promising candidates for understanding the diversity and resilience of life in the universe. The exploration of this distant moon continues to inspire curiosity about the origins of life and the potential for habitable worlds beyond Earth. Enceladus, a small icy moon orbiting Saturn, has become one of the most intriguing objects of study in our solar system due to its remarkable geological activity and the compelling evidence suggesting the presence of a vast subsurface salty ocean beneath its icy crust, which is believed to be heated by the intense gravitational interactions with Saturn and other nearby moons, causing cracks and fissures through which plumes of water vapor, organic molecules, and other organic compounds are continuously ejected into space, providing a rare opportunity for scientists to analyze the composition of its hidden ocean without having to drill through miles of ice. These observations not only indicate that Enceladus has the necessary ingredients, liquid water, chemical energy, and organic molecules that could potentially support microbial life, but also point to active hydrothermal processes at the ocean floor, similar to Earth's deep-sea vents, which could create a habitable environment with energy sources suitable for life. Combined with the moon's relatively small size and the abundance of organic-rich materials detected in the plumes, these factors make Enceladus one of the most promising locations in our solar system to search for extraterrestrial life, prompting plans for future missions that aim to directly sample the plumes, analyze their chemical and biological contents, and explore the ocean's conditions in greater detail to assess its potential habitability and expand our understanding of where life might exist beyond Earth. And so, Enceladus remains suspended in the outer darkness of our solar system, small, silent, and glistening with secrets frozen into its shell. Secrets that whisper to us through the towering plumes erupting from its fractured surface. What once appeared to be just another icy moon among Saturn's countless satellites has now emerged as one of the most compelling beacons of hope in the quest to find life beyond Earth. With every molecule hurled into space by its geysers, Enceladus offers us a fleeting glimpse into a hidden ocean, rich in organic chemistry and warmed by the immense gravitational tides of its parent planet. There, in that pitch-black saltwater world beneath the ice, where no sunlight can ever reach, the ingredients for life as we know it silently coexist: water, energy, and complex carbon-based compounds, all locked in a stable, active system that has persisted for possibly billions of years. And if life has emerged in that dark sea, it may not be life that builds cities or gazes at stars, but simple, alien organisms that drift near hydrothermal vents, sustained by chemical gradients, just as Earth's earliest life once was. The idea that something is alive, right now, swimming beneath the frozen crust of a distant moon, is more than just science. It's a revolution in how we understand life itself. It reminds us that biology does not belong to Earth alone, that the cosmos may be full of living worlds hidden in the most unlikely places. Enceladus teaches us humility, awe, and possibility. It turns our eyes from the stars to the icy shadows and says, here too, there may be life. As new missions are dreamed, as future spacecraft are designed to fly once more through its ethereal plumes or even land softly on its frigid crust, we are compelled by more than just curiosity. We are driven by a timeless question encoded in our DNA. Not just whether we are alone, but whether life is a cosmic inevitability rather than a miracle. In the silent language of vapor and molecules, Enceladus answers with a whisper, urging us to return, to listen, to explore. Because in that tiny moon, orbiting a gas giant in the cold abyss, we may find not only the first signs of alien life, but the next chapter in the story of our own. Ganymede, the largest moon in our solar system, is a remarkable celestial body that has fascinated scientists for decades due to its extraordinary size, complex magnetic environment, and the presence of a vast subsurface ocean. With a diameter of about 5,268 kilometers, 3,000, one of Ganymede's most distinctive characteristics is its intrinsic magnetic field, which is generated by a liquid iron or iron sulfide core within the moon. This magnetic field is unusual among moons and is thought to be produced by a dynamo effect, a process similar to Earth's magnetic field generation, caused by the convection of electrically conductive fluid inside its core. The magnetic field extends far into space, creating a complex magnetosphere that interacts dynamically with Jupiter's powerful magnetic environment. This interaction results in brilliant auroras near Ganymede's poles, similar to Earth's northern and southern lights, but far larger and more intense. The magnetosphere also shields parts of Ganymede's surface from charged particles and cosmic radiation, influencing the moon's surface chemistry and the potential habitability of its subsurface environment. Beneath its icy crust, which is estimated to be between 150 and 250 kilometers thick, Ganymede hosts a vast internal global ocean of liquid water, making it one of the few places in our solar system where a substantial underground aquatic environment exists. This subsurface ocean is believed to contain more water than all of Earth's oceans combined, hidden beneath layers of ice that are kept in a liquid state through a combination of heat sources. These heat sources include radioactive decay within the moon's interior and tidal heating caused by gravitational interactions with Jupiter and other Galilean moons such as Europa and Io. The intense gravitational tugging stretches and flexes Ganymede's interior, generating enough heat to maintain the ocean in a liquid state over geological timescales. The presence of this vast, salty and potentially mineral-rich ocean raises exciting possibilities about the potential for life to exist beneath the icy surface, especially considering the chemical interactions that could occur at the ocean-rock interface. The surface of Ganymede is a mosaic of highly reflective icy plains and darker, more cratered regions, featuring a complex pattern of grooves and ridges that indicate tectonic activity and the continuous reshaping of its icy crust. These surface features are evidence of the moon's geological dynamism, driven by the internal heat and the gravitational forces exerted by Jupiter. The surface also contains a variety of minerals, including salts and other compounds that have been transported from the interior to the surface through cryovolcanism and other geological processes. The combination of Ganymede's magnetic field and its subsurface ocean makes it a prime candidate in the ongoing search for extraterrestrial life within our solar system. Scientists believe that if life exists elsewhere beyond Earth, it would most likely be found in environments where water, energy, and essential chemical building blocks are available, conditions that Ganymede's ocean could potentially provide. Future missions, such as the European Space Agency's JUICE, Jupiter Icy Moons Explorer, and NASA's upcoming efforts, are planned to explore Ganymede in greater detail. These missions aim to analyze its surface composition, map its magnetic field, and, crucially, sample the composition of its atmosphere and possibly its ocean through ice-penetrating radar and other remote sensing techniques. Such investigations hope to determine whether Ganymede's hidden ocean could harbor the ingredients necessary for life and to better understand the Moon's geological and magnetic processes. Ganymede is a fascinating world that combines immense size, a complex magnetic environment, and a vast internal ocean, features that make it one of the most exciting targets in planetary science and astrobiology. Its unique properties not only deepen our understanding of moon formation and planetary magnetism, but also hold the tantalizing possibility that beneath its icy exterior, conditions might exist that could support life, making it a key focus for future exploration and discovery in our quest to understand the potential for life beyond Earth. The Io, one of Jupiter's 4 largest moons and the most volcanically active body in the solar system, presents a striking and dynamic example of planetary geologic activity driven by intense gravitational interactions. Its extreme volcanism and the tortured state of its interior are primarily caused by the powerful gravitational pull exerted by Jupiter, combined with the effects of the Moon's orbital resonance with other Galilean satellites such as Europa and Ganymede. At the heart of Io's volcanic fury is the process of tidal heating. As Io orbits Jupiter, its path is slightly elliptical rather than perfectly circular. This elliptical orbit causes the Moon to experience varying gravitational forces from Jupiter, which stretch and flex Io's interior repeatedly. Each time Io moves closer to or farther from Jupiter during its orbit, the immense tidal forces generate immense frictional heat within its interior. This continuous flexing prevents Io's interior from cooling completely and leads to the melting of rocks and the formation of extensive magma chambers beneath its surface. The result of this intense internal heating is an active and constantly changing surface marked by hundreds of active volcanoes, volcanic pits, lava flows, and plumes that can reach hundreds of kilometers into space. These volcanic eruptions release sulfur, sulfur dioxide, and other volcanic gases and materials, creating a colorful and ever-changing landscape. Some of the most famous volcanic features include the towering lava fountains of Pele, the large volcanic caldera of Loki, and the persistent volcanic plumes that sometimes extend several hundred kilometers above the surface. Io's interior is believed to be in a state of ongoing deformation and differentiation due to this vigorous tidal heating. The intense internal heat source causes widespread melting of rocks, maintaining a partially molten mantle and possibly a liquid core. This geological activity not only fuels its surface volcanoes, but also contributes to its extreme geological dynamism, with frequent resurfacing events and a lack of impact crater preservation on much of its terrain, indicating a relatively young and constantly renewed surface. The tortured interior and extreme volcanism of Io are unique in our solar system, making it a natural laboratory for studying planetary heating processes, volcanic activity, and the effects of gravitational interactions on planetary bodies. The ongoing volcanic activity also releases significant amounts of sulfur and other gases into Io's thin atmosphere, which is constantly replenished by volcanic plumes. These features, combined with Io's intense heat and energetic volcanic eruptions, exemplify how gravitational forces can power and shape planetary geology in ways vastly different from terrestrial processes driven primarily by radioactive decay or residual heat. Io's extreme volcanism and its tortured interior are direct consequences of Jupiter's powerful gravitational influence, which induces intense tidal heating through orbital flexing. This process sustains a highly active volcanic landscape, continuously reshaping the Moon's surface and internal structure, and provides a vivid illustration of how gravitational forces can drive geological activity in planetary bodies across our solar system. Callisto, one of Jupiter's largest moons and the third largest moon in the solar system, is renowned for its incredibly ancient and heavily cratered surface, which has remained remarkably unchanged for over 4 billion years, effectively making it a natural time capsule that preserves the history of the early solar system. Its surface is a complex mosaic of dark, heavily cratered regions interspersed with lighter, relatively younger terrains, indicating that the Moon has experienced little geological activity to erase or modify these features since its formation. Unlike some of its neighboring moons, such as Europa or Io, which display signs of active geology through tectonic movements, volcanic activity, or intense resurfacing, Callisto's interior appears to be relatively inert, with minimal internal heating and little evidence of ongoing geological processes. This inertness suggests that its icy crust and internal structure have remained largely static over billions of years, allowing impact craters to accumulate and be preserved almost perfectly, providing scientists with a detailed record of impact events and the environment of the outer solar system during its formative years. Despite its apparent dormancy, recent research and models propose that beneath Callisto's thick ice shell there may exist a subsurface liquid water ocean, which, if confirmed, would make it a candidate for potential habitability, similar to Europa and Ganymede, albeit less geologically active. What makes Callisto truly unique within Jupiter's moon system is this combination of an ancient, heavily cratered surface that has remained largely unchanged due to its inert interior, paired with the possibility of a hidden ocean beneath its icy crust, offering a pristine record of early solar system history while also presenting an intriguing environment for astrobiological studies. Its lack of significant tectonic or volcanic features, along with its stable surface and potential subsurface water, makes Callisto an invaluable natural laboratory for understanding planetary formation, impact history, and the potential for life in icy worlds, standing out as a fascinating subject for future exploration missions aimed at uncovering the secrets of our solar system's distant past and the potential habitability of icy moons. Far beyond the orbit of Saturn, deep in the icy outskirts of our solar system, orbits a moon that defies expectation and rewrites the rules of planetary science. A world called Triton, Neptune's largest moon, and one of the strangest places we have ever glimpsed. Unlike any other major moon in the solar system, Triton moves in retrograde, orbiting Neptune in the opposite direction of the planet's rotation. A clear sign, scientists believe, that it was not born there, but captured, possibly long ago, from the distant Kuiper Belt, where icy dwarf planets and ancient comets silently roam. This violent capture may have reshaped both the Moon and its parent planet, disturbing Neptune's original system and sending other moons tumbling into chaos. But Triton itself, despite the cold and distance, remains hauntingly active. When Voyager 2 flew by in 1989, the only spacecraft ever to visit, it saw something no one expected. Cryovolcanoes, geysers of liquid nitrogen and other ices erupting from the surface, spraying dark particles miles into space before they fell back like snow, creating streaks and stains on the Moon's pale, frozen plains. These were not fire and lava volcanoes, but icy ones, driven by internal heat and volatile materials beneath the crust. That heat, combined with a relatively smooth surface and hints from gravity measurements, has led scientists to believe that a subsurface ocean may still slosh beneath Triton's frozen exterior, an ocean locked under miles of ice, kept warm by tidal flexing and the lingering heat of its violent past. If this is true, Triton could be more than just a frozen relic. It could be a cradle for life, harboring the same key ingredients seen on Europa and Enceladus: water, energy, and possibly the organic molecules needed for biology to spark. Its thin atmosphere of nitrogen, its complex surface of icy ridges and cantaloupe terrain, and its retrograde path through Neptune's shadowed realm all add to its enigma. Triton is a paradox, young yet ancient, captured yet dynamic, frozen yet possibly alive inside. It is a ghost from the solar system's chaotic youth, carrying whispers from the Kuiper Belt and secrets from an ocean we cannot yet see. And though only one spacecraft has ever come close, Triton calls to us still, beckoning explorers to return, to drill beneath its surface, to decode its chemical messages, and perhaps to uncover signs of life in the farthest, coldest reaches of the Sun's domain. In Triton, we are reminded that even the loneliest worlds may still be alive, still evolving, and still waiting to be understood. Triton, Neptune's largest moon, is one of the most intriguing bodies in our solar system due to its unique characteristics and complex history. It orbits Neptune in a retrograde direction, meaning it travels around the planet in the opposite direction of Neptune's rotation. This unusual orbital behavior strongly suggests that Triton did not form in place with Neptune, but was instead captured by the planet's gravitational pull at some point in the distant past. Many scientists believe that Triton was originally a Kuiper Belt object, similar in composition and origin to Pluto and other icy bodies located beyond Neptune, that wandered too close to the planet and was gravitationally ensnared, becoming a satellite. This capture process likely occurred billions of years ago, and the Moon's current orbit is highly elliptical and inclined, consistent with an origin as a captured object rather than a native satellite. Triton's surface is a testament to its dynamic geological history. It is characterized by a relatively young and active terrain with vast plains, ridges, and a variety of surface features that indicate ongoing geological activity. One of the most distinctive features on Triton is its cryovolcanoes, volcano-like structures that erupt volatile substances such as water, ammonia, or methane instead of molten rock. These cryovolcanoes are evidence of internal heating and geological processes that have reshaped Triton's surface over time. Unlike terrestrial volcanoes, cryovolcanoes eject icy materials and gases, forming geysers and plumes that can extend hundreds of kilometers into space. The eruption of these substances suggests that Triton's interior remains geologically active, driven by internal heat sources, possibly derived from tidal heating, where gravitational interactions with Neptune generate friction and heat within the Moon's interior. Beneath Triton's icy crust, many scientists hypothesize the existence of a subsurface ocean, a vast layer of liquid water that could be kept in a liquid state by internal heat and the presence of antifreeze compounds like ammonia. This subsurface ocean is particularly compelling because it might provide a habitable environment where microbial life could potentially exist, making Triton an object of astrobiological interest. The presence of nitrogen-rich ices, geysers, and cryovolcanoes further supports the idea that Triton has a complex internal structure and active geology, with heat and materials cycling between its interior and surface. Theories about Triton's origin and evolution are still evolving, but its retrograde orbit and geological features strongly support the idea that it is a captured object, likely originating from the Kuiper Belt. Its capture would have been a violent and tumultuous event, possibly involving gravitational interactions with other bodies or even collisions, which would have imparted significant energy and could have contributed to its current orbit and internal heating. Over billions of years, Triton's orbit has likely stabilized, and its internal activity may have persisted, driven by residual heat from capture and radioactive decay. In summary, Triton is a captivating icy moon with a complex history of capture, internal activity, and potential habitability. Its cryovolcanism, possible subsurface ocean, and retrograde orbit make it a key target for future exploration. Studying Triton provides valuable insights into planetary capture processes, the evolution of icy bodies, and the potential for life in subsurface oceans beyond Earth. As future missions are planned to explore Neptune and its moons, Triton remains a prime candidate for uncovering the secrets of our solar system's distant and icy frontier. Venus, often referred to as Earth's twin because of their similar size and composition, is one of the most fascinating and extreme planets in our solar system. Despite their similarities in size and structure, Venus is a world of stark contrasts, showcasing environments that are almost unimaginably hostile to life as we know it.